Hi, my name is Justin Pahoni. Welcome to this course on the fast and easy to use framework sweeping the big data world, Apache Spark. Why do we even need a framework for processing big data? We have grep or some other custom scripting tool for processing our data, right? It's simple and relegated only to the complexity that one machine requires. Well, that might be a problem. How do we deal with the ever-growing data that has become big data? Data that might not even logically fit onto one machine. Or even if it does, the time to process begins to slow down as the size of the data increases. Okay. You say that's the problem MapReduce was built to conquer, parallelizing the processing across a distribution of machines, taking the processing to the data, solving that big data problem by throwing it against big processing power. Okay, sure, this sped up big data's processing by orders of magnitude in comparison to the previously mentioned single machine algorithms. And yeah, this has worked pretty well for a long while, but it has a multitude of difficulties. Algorithm complexities, disk bottlenecks, and not being able to perform more than just batching, to name a few. In comes Spark to the rescue, which uses a number of optimizations that allows it to perform those same Hadoop computations against a fraction of the resources while still running yet another magnitude faster. In fact, at the end of 2014, Spark officially beat the existing on-disk file sorting benchmark, performing 3 times faster than that previous mark, using about 10 times less machines. Taking it one step further, Spark even ran the sort against a petabyte of data and, keeping a constant rate, was able to decimate any previous sorts of that magnitude. And it has continued to dominate the field ever since. But wait, that's not all. Processing time and power are not the only things that Spark shrinks. With Hadoop, big data also means big code, shown by this simple word count example. But big data does not have to mean this clunky beast, as can be seen by this equivalent Spark code. Even within the code itself, the main logic can be discerned in these 4 lines, whereas the MapReduce logic is here, here, and here, muddled throughout the code in between a sea of boilerplate. These reasons by themselves should be enough to persuade you to choose Spark, and we've only just scratched the surface. As we saw, Spark's generalized abstractions result in tinier code, which increases readability, and, along the same vein, those same properties end up allowing for more expressive code. And we've also discussed how Spark has many mechanisms that allow it to speed past its competition. Even our earlier news bulletin was simply computations against disk, whereas Spark made its initial waves as a computation engine that could work off of cached data in memory, taking advantage of the speed that brings, and blow past the competition. We'll see this and other means of Spark's speed throughout the course. Going back to the gains won by a generalized abstraction, testability becomes just about as trivial as any other code you might write. This is because you can write code as if it isn't distributed, only worrying about such things at deployment time. Separation of code from deployment also means that you can now directly interact with your data from your local machine, figuring out your algorithms on the fly in near real time. This allows you to start with your prototype, building it into production code, and scale up and out as your processing requires. This even means that you can debug most problems off of a local sample set, growing the code quickly and seamlessly. And any big data processing worth its salt should have fault tolerance built right into the model, as Spark has done from its conception. Last, but definitely not least, is that Spark unifies different types of big data needs. Whether you're processing batch data or streaming data, pushing it through graphing or machine learning algorithms, the Spark toolbelt has something for you, along with different means to visualize said data. Alright, now that you have a better understanding of why we need Spark, let's take a quick step back to review the course structure. In this first module, we'll continue with the basics of Spark and its rapid rise to be the biggest big data open source project out there. Then, we'll dive into the core framework, creating a solid groundwork for writing your own big data program. We'll follow that with a look into cluster managers and the many ways that Spark can be deployed, which will lead into a proper discussion on how to best maintain a Spark program and deployment. That'll leave you with a solid backing towards your first full-fledged Spark application. At that point, you'll be ready to step into learning about Spark's next level of APIs. The libraries built on top of the core: Spark SQL, Spark Streaming, and MLlib and GraphX. Note that while this will be a good start for the libraries, I highly suggest heading over to this course's natural follow-on, handling fast data with Apache Spark SQL and streaming. As titled, it takes what you learn in this course and expands the SQL and streaming side of Spark, which are now the de facto starting points for a modern Spark application. And to complete the course, we'll learn about a number of problems that often crop up in Spark applications and how to handle them and even get ahead of them, ending with a glimpse into Spark's brilliant future. With regards to the module you're already in, we'll review how Spark compares with Hadoop, traversing the history that led to Spark becoming such a big data powerhouse. Then we'll review how to get Spark onto your machine and dive into a quick demo of its power using the hello world of big data, counting words. And finally, we'll finish this section by preparing ourselves for the rest of the course and the overarching project that we'll work through. A quick note on these next two sections. They'll be discussing Spark's background, past and present, and aren't necessary to learn the framework. If this is not of interest to you, then you can head directly over to the installation section. Now, we've seen how Spark shrinks processing time, machine resources, and code when compared to Hadoop. But there's one other problem that it solves: the MapReduce explosion. The explanation for what this is comes from Jon Stoica, executive chairman of Databricks, the company commercializing Spark, which we'll discuss further in the next section. He talked about how the first cell phones were clunky and led to a wide array of specialized gadgetry, similar and complementary. But then the smartphone came along and united all of that chaos into one easy-to-use device. So, in the same vein, we know that the original big data processing problems were alleviated by the advent of Hadoop. And in the early years, it was a big leap in technology. However, I think Tim Tolley of Yahoo put it best when he said that MapReduce is like pushing a square peg through a round hole, meaning that it's very restrictive in its design as it has a very narrow focus specifically on batch processing. This overspecification led to an explosion of specialized libraries, each adding a new API to juggle in your big data mental model, each attempting to solve different problems. So, say you want to process streaming data at scale, then you'd have to use another complementary library called Storm. Then, you decide you want to try to get rid of some of the cruft around the MapReduce boilerplate, so you might turn to Scalding. Or you may find it easier to query your data using something like Hive. And the list of specializations needed to work through an entire Hadoop workflow goes on and on and on. So, along came Spark's generalized abstractions for big data computing, bringing the big data pipeline back to one cohesive unit, just as the smartphone in the original example. Spark's aim is to be a unified platform for big data, an SDK for the many different means of processing. And it all originates from the core library, which means any of its extension libraries automatically gain from improvements to the core, including performance boosts. And due to the core being so generalized, extending it is fairly simple and straightforward. If you want to query your data, just use Spark SQL library. If you want to stream, there's a streaming library to help you out. Even machine learning is made more straightforward with MLlib. And GraphX does the same for graph computation. On top of all that, the Spark contributors have even brought some of these concepts together using the newer DataFrames/Datasets API, continuing to unify the ecosphere. The course will cover this entire Spark ecosphere with its deepest focus being on the core library, which is what all the other libraries extend, only adding to it where their specialization specifically deviates. And, as previously mentioned, my follow-on course to this one, handling fast data with Apache Spark SQL and streaming, expands the basics of the most important libraries, SQL and streaming. So, how did we get to this powerhouse of big data unification? We've already talked about MapReduce, which was popularized in 2004 when a paper on the subject was released to the public. That and other ideas led to the birth of Hadoop at Yahoo in 2006. But, as we've already mentioned, that was only the beginning of modern big data computation, as 2009 brought along Matej Zaharia and his creation as a PhD at UC Berkeley, namely Spark. Then, in June of 2010, he released his research paper on the project, titled Spark, Cluster Computing with Working Sets, following up later that year by releasing the project as open source under the BSD license. The project began to gain ground while still being incubated in Berkeley's AMP Lab as part of the Berkeley Data Analytics Stack, or BDAS for short. The AMP Lab was created as a 5-year endeavor starting in 2011, spun down at the end of 2016, rolling into the real-time security-focused RISE Lab. Its goal was to find the best solutions for these big data problems, focusing on algorithms, machines, and people, thus AMP. And Spark fit that agenda well. It continued to pick up some real momentum in the community, and in 2013, Matej and a number of the prominent Spark collaborators founded Databricks, a company focused on supporting Spark as an open source product and commercializing parts of this burgeoning big data world. Keeping up momentum, that same year, Spark switched its license to Apache Commons 2.0, very quickly graduating to a top-level Apache project as of 2014. That same year brought Spark the record for large-scale data sorting, as mentioned earlier. Then, in 2016, the 2.x branch of Spark was released, making sure it remained up-to-date in this ever-changing world of technology. And, as it's still one of the most active big data projects, it continues to grow and break down any big data walls in its way. Its Apache licensing and the founding of Databricks is a big part of its growth, as it provides certain assurances to enterprises that Spark will be a stable framework to utilize. While the Spark community is very active, a vast number of the improvements for Spark do still come from those within Databricks, and they've set their focus on continually improving Spark while keeping it stable. In fact, everything that is not marked as an alpha product or a developer API in a major version of Spark should be backwards compatible, even with an attempt at binary compatibility within that branch, which means that a Spark upgrade would not require rebuilding your project. And even within any alpha project, breaking changes are clearly documented as part of their documentation of each release. They take such precautions in this vein that they've even built a custom tracker which causes any breaking changes in the API to result in a build failure, as well as prominently display any new public classes added by a change set. As of this recording, I believe this is one of a kind for open source automated build systems. As far as the versioning itself, they keep a structured, reliable build schedule, building a new minor release every 6 months, favoring consistency of time over features. Any features that don't fit in the 3-month time frame will simply fall to the next release. Of course, there's a slight caveat with that, in that each new release must go through the Apache voting process. However, that hasn't caused any notable slowing of the cycle as of this recording. These releases often contain new features, while patch releases are used to keep past versions up to date on a less strict schedule, making sure that any important bugs are squashed along the way. This dedication to reliability, stability, and performance has not only helped bring a dedicated community of contributors, but also an ever-growing community of users. Spark's generalized abstraction and growing helper libraries mean that companies can use Spark for a vast number of usages, such as Pandora's real-time recommendation system. Recommendations and other personalizations using big data are definitely a vast use case, covering companies such as Yahoo, Comcast, Ooyala, Conviva, and Netflix. In fact, Netflix even tested Spark against Chaos Monkey to check its resiliency, and they were happy with the results, excited to take it to the next level. Another case is with the load of data crunching for real-time threat analytics, such as different types of fraud detection. And of course, there's the case of log aggregation and analysis being done at eBay. Then, there's Twitter's usage for graph analysis of social networks. And my, along with many others' favorite usage is the many areas of science exploration, such as Freeman Lab at Genelia, where they're using Spark for analyzing and visualizing patterns of brain activity in real time. Big data has already helped towards difficult medical diagnoses and could lead towards curing diseases such as cancer. Spark's usage seems to only be limited by the extent of your imagination. You need to choose what type of distributed file system you'll be running against. Or you can choose to grab the source code directly so that you can make any modifications and/or build against a file system that isn't pre-built. We'll choose the version that targets the latest version of Hadoop for the course. However, bear in mind that there are packages for different Hadoop versions, as there are often changing protocols across versions that break binary compatibility. So, if you have an existing Hadoop system you're planning to target, then you'll need to make sure to pick the right version. You can check that through the Hadoop command line using Hadoop version if you aren't certain. Once you've made your selections, you can click on the Download Spark link and the suggested mirror, which kicks off the download for the Spark package. Once downloaded, you'll need to untar it to get to the underlying Spark folder. I'm going to use 7-zip to extract it to my C drive, but any extraction tool will work. Now, if you chose a pre-built version of Spark, then the only additional item you need is to have the Java Development Kit, or JDK, installed. For this course, I'm assuming that you already have this set up, and if not, it's as simple as Googling for JDK and following the links. One other setup that is more of a nicety is to add the bin folder located in the Spark root to your environment path so that you can directly access some of the helper utilities without having to always specify the full path. If you've done that, then you should be able to test that your install was successful by running spark-shell from your command line of choice. If everything is installed correctly, then you should see the Spark graphic along with the version you have installed. And one other quick aside is that Spark has a number of points where it looks for its root directory, which can be helped by setting the Spark Home environment variable to point to your Spark root. There are two additional notes on Spark installation. The first is to point out how to change the logging verbosity, in case you need to increase or decrease it. The information that Spark outputs can be very useful when running into hard-to-debug problems. In the normal case, we don't need it though. Now, let's change to only caring about error output. So we'll head to the conf folder, which houses a number of useful configuration templates. For now, we're just going to focus on the log4j one, as log4j is the logging utility being used within Spark. So, we simply copy this file into the same directory, open it, and change all logging to error so that only an error message will be output. Then we save it and remove the .template. Now, when we rerun Spark shell, the output will be much more manageable. The final note is for those who will be running their shell against a Windows environment. You may have noticed this fairly large error that I got whenever I ran the shell. As of this recording, there's an open Spark bug, Spark-2356, which is really a Hadoop bug, which results in exceptions when working with the Windows file system. To remedy this, you'll need to add winutils.exe to your Spark bin directory. The executable is included in the demo files for this course, but can also be obtained by going to that Spark ticket 2356. In the comments, there are actually multiple links that will result in this executable's downloadable location. Last, head back to the system's environment variables and add a Hadoop home variable to be the location where the bin/winutils.exe is located. In my case, this is C:/Spark. Once set up, Spark will be able to work with the Windows file system. As you can see by the error no longer displaying. With a local Spark environment set up, we're now ready to begin playing around with some code. However, before we do, let's take a step back and review the programming languages at our disposal with Spark. You heard me. There's more than one language possibility for writing a Spark application. In this course, we'll use the language in which Spark itself is written, Scala. So, if you don't have any background in Scala, now might be a good opportunity to head over to one of my other courses, Scala GettingStarted. But, even without any Scala knowledge, my aim is to make the code used throughout this course understandable to anybody who at least knows a programming language. But I did say that there were other language avenues for writing a Spark application. The most obvious one is Java, as any Scala library, such as Spark, is also compatible with Java, albeit through a more verbose syntax. Even such verbosity is toned down due to an effort by the Spark developers to keep clean APIs, resulting in an uncluttered Java API. And Spark also supports Python, although there are some parts of Spark that aren't at full feature parity when using the Python library. The majority of the time, you won't even miss the gaps, which are constantly being filled anyway. And as of its 1.4 release, Spark even supports another big data language that's catching fire, R. So, Spark covers a vast portion of the big data language spectrum, making it easy to use whatever language you feel most comfortable. As already mentioned, I'll be using Scala, but I'll try to point out any severe deviations for the Java and Python libraries. Due to Python's dynamic nature, its API mirrors the original Scala one the best, and shouldn't require much, if any, intervention. But the Java API is more verbose and has some extra hoops to jump through. In those cases, I'll definitely take a moment to discuss how the methods being taught can be translated into the Java equivalent. Overall, the API signatures between the languages are fairly consistent. So, as long as you understand the concepts and which method is most useful for a given scenario, you should be able to translate to any of the possible Spark languages. To the code. Of course, it's customary when exhibiting a big data framework for the first code to be the hello world of big data, counting words. As we've already briefly seen during installation, Spark comes with a shell that can be used to run interactive queries. A short tutorial on interacting with a shell like this can be found in my Scala course in the first modules section named The REPL, Getting Immediate Feedback. In fact, the Spark shell is the same one used for regular Scala applications, except with some minor modifications. It's how Spark is able to bring interactive querying to big data. The ability to test your code and get immediate feedback is very powerful for building applications iteratively and quickly, which is why we'll be using it for a number of the samples throughout the course, where a discrete, focused example will best display the properties of the method being described. Now, let's boot it up by typing spark-shell in the command window, as we did during the installation section. The first thing to notice is that the shell automatically creates two values for you, one named SC and the other Spark. Spark is typically used for the Spark SQL library, so we'll return to that in a later section. SC, on the other hand, is the main starting point of a Spark application, a Spark context. Thus, the name of SC. All Spark jobs begin by creating a Spark context, which will act as the delegator of many aspects of control for the distributed application. We'll dive into more of the details on Spark contexts in the next module. For now, we'll use the one which is supplied to us by the shell construction. We'll start by telling the context that we want to load a file using its text file method and storing the results in a value, text file. For simplicity, we're using the README file that's packaged at the root of the Spark distribution. Note the file location may be different depending on where you extracted Spark to. We immediately get our result in the form of an RDD, the most basic abstraction of Spark. It's called an RDD because it's a resilient distributed dataset. However, it's just what I said, an abstraction of the operations we're declaring. That's why we saw immediate feedback. All we did was tell the context our intent of loading the file. Spark's core operations are split into two categories, transformations and actions. Transformations are lazily evaluated, only storing the intent. It isn't until an action is executed that the results are actually computed, as we can see by executing the first method, an action which retrieves the first line of the text file. Now, we see an actual result, a string containing pound Apache Spark. There are many benefits to Spark's laziness. In this case, we didn't need to read the entire text file, only the first line. Had this not been lazy, then we would have loaded the entire text file only to realize that all but the first line could be dropped. These optimizations are very important when working with truly big data, which is why we'll come back and discuss this further in the next module. For now, we'll go back to the text file value to map each line of the file, splitting it into an array of space-delimited words, and flattening the resultant sequence of string arrays into a single long sequence. So we now have a new RDD. However, this time the strings it represents are not the lines of the file, but instead all of its words. So, we now need to set up our sequence for counting by changing each word into a key-value pair where the word is the key and the value is the count, seeding with an obvious count of 1 for each uncounted word string. With the data prepared into this key value format, we can now reduce the values down to a single count for each key, adding up all the ones in each word bucket. And what use is a word count if we can't see it in sorted order? Here, we're simply sorting our list of word count pairs on the count in descending order. The _2 is simply Scala's way of accessing the object in the second position of a tuple, which is how this key value pair is being represented, as a tuple 2. All of this has been a chaining of a number of transformations on our data, so the lazy nature of transformations means that none of the data has been processed yet. So, let's go ahead and write this out to a file by calling the action save as text file, passing in the path where we wish to save the data. If we go to that path, we'll see not a text file, but a folder of that name. That's because this is written out as Hadoop distributed. So, to see our data, we can go into the folder and review all of the parts, where the number of file parts equals the number of partitions that our dataset was distributed across. Notice that the ordering is preserved, with the first file containing our largest items, and the second continuing through the list. This ordering would be maintained no matter how many partitions were used. The data would just be split into more files, which would be distributed across a number of machines in the normal production case. We'll dig more into the mechanics of this in the next module. But now that we've seen the map and reduce way of counting words in Spark, let's see an even simpler way. The pattern of mapping into key value counts and reducing the values for counting is so common that there's an API method for it, count by value. It combines the map and reduce by key into one well-named method. Spark is no different than any other framework. Half the battle is knowing your arsenal in the form of all the different API methods. It can keep you from over or underkill by using the right method for the job. We'll discover many other hidden gems just like this throughout the rest of the course. Before we dive into Spark's core library, just a few housekeeping items. First, when it comes to big data itself, we know that tools like Spark are more useful than ever, as data can be found everywhere. The Internet of Things means that we aren't using these tools just for social graphing computations and enterprise purposes, but they're now useful for things like constantly personalized data. In fact, this abundance of data is said to be growing faster than computation power, per Moore's law. So, being able to write succinct, distributed programs is more important than ever. However, it's important not to get too carried away with this power. Make sure you think about your data and whether it's truly big data. Tools like MapReduce and Spark are great for big data. But a simple command line tool is sometimes capable of processing fairly large sets of data in a more efficient manner. Simply make sure to think about other possibilities for how your data could be processed and choose the right tool for the job. That being said, as previously discussed, Spark's unified model of combining processing with machine learning, streaming, and other utilities brought by its libraries often means a complete workflow can all be attained within Spark. So, that might be enough of a reason in and of itself. Just make sure to think through all of your possibilities. And even more, while Spark was originally built to target Hadoop, it has grown past that and is now a general-purpose computing framework that's capable of handling many different distributed systems. Next, the course is partially going to be set up so that we'll slowly build a big data project which runs through a dataset of writing samples that we'll use to calculate synonyms and even solve analogies. The data corpus I'll be using is a sampling of wiki pages, but any collection of documents will do the trick. This project will be built alongside a number of separate, smaller examples that might better exhibit a certain portion of the API, like streaming the top hashtags from Twitter. All along the way, we'll obviously be learning the ins and outs of Spark, keeping in mind that it's still a very active community. This means that any experimental or developer methods of the API which are well documented, are subject to change between the time of recording and the time you might be viewing it. I'll make sure to be explicit about these methods though, as well as if I know the version a feature was introduced, I'll point it out so that you don't look for it in an older version where it might not exist. We won't be diving into any alpha component libraries, so we should only need to focus on the possibility of change at the method level. Finally, Spark makes unit testing so easy and similar to any other program you might write that I'll only be focusing on the Spark API and not how to test it. If you're looking to strengthen your unit testing skills, Pluralsight has a number of courses on unit testing, ranging from my own Patterns for Pragmatic Unit Testing to Mark Siemens' Advanced Unit Testing. In the last section, there were some points that have correlated blog articles that I would suggest perusing. First is Jan Stoika's article on how big data and Moore's law are closely related. Then, there are two thought pieces on when to use big data tools or not to use them. The first gives an idea of what's considered big data, and the second is a comparison between big data tooling and a simple command line script. As mentioned in the last section, it's important to at least think about whether a big data framework such as Spark is the right tool for the job. Now, let's cover some more general resources that'll be useful to help continue your Spark learning following the completion of this course, or just help you find quick answers to any future Spark questions you may encounter. The Spark community has done an awesome job of maintaining a very useful array of information on the framework, much of which can be found through its website, spark.apache.org. There's a general page for overall documentation, a page for specific pieces of documentation, a page describing some of the best ways to get in contact with the active Spark community, and even a page containing some basic code examples. Beyond the Spark website, there's also the Learning Spark book published by O'Reilly and written by some of the most prevalent Spark contributors. And, of course, remember that Spark is an open source project on GitHub, so if in doubt, you can always read through the source code. There are benefits to it being a smallish codebase. Many parts aren't too complex to understand just by the code itself. So, as we've seen, there's a lot of additional documentation out there to aid you once you've gone through this course. I've condensed a vast array of the most useful pieces into the course itself, but as I've already mentioned, this is an active community, meaning there's constantly new pieces and features being added. In this introductory module, we started off by learning why Spark is needed, citing its ease of use, speed, and fault tolerance, to name a few. Then we saw how Hadoop's MapReduce was merely a base for big data computation, leading to a slew of specialization frameworks, which Spark came along and unified for an easier mental model. We then had to learn how it was created, where it is today, and a glimpse into its future, which we'll dive into more details at the end of the course. And to get set up for the rest of the course, we ran through the installation and the hello world of big data in the form of a word count example, closing this portion with a lead on some useful resources you can use after you've gained a head start from the rest of the course.